Greeting, fellow data folks. My name's Steve, and today I'm going to be giving you a speedy 10-minute introduction to vector databases. The agenda for today, we're going to talk about what are vector databases, differentiate them from relational databases, and then we're going to talk about some places where they make sense. So let's get started right away with what is a vector database? They're relatively new, so most people probably don't know what they are. The easy answer is a data store that works with vectors, but that's not very helpful. To answer this, let's first talk about what we mean by vector, sometimes also called embedding. So if you have done some AI ML work, you have probably heard about embeddings. If you haven't, don't worry, you'll learn about vectors, which are embeddings. Vectors is all about turning things into numbers. And what I mean by things usually is unstructured data, like a long body of text, an audio recording. You can also make vectors with numbers as well, but right now we're seeing it mostly around unstructured data. And that's because numbers are really easy for computers to understand. So they can turn them into bits and then do stuff with them. Like they can say 2 is less than 3, or you can assign a character to have a certain number, and then you can say A is less than B. You can do all those things once you get to numbers. But what do you do with something like pictures, right? How do you actually do comparisons? You can say, is this picture equal to this picture? But it's hard for the computer to know what else to do with that picture besides equals, because you have to turn it into some sort of meaningful numbers. And that's where vectors come in. Vectors are basically taking a picture, feeding it through a neural network, and then coming out with a vector that actually has semantic meaning or meaning for the photograph. So in this example, we would take this nice kitty and we would turn them into a long array of numbers, basically all the pixels laid out in a big array of numbers. You feed that into the neural network. The neural network learns what are the significant features in that long array of numbers. And then from there, it outputs a much smaller array of meaningful vectors or meaningful numbers that are the vector. And while I'm using a picture of a cat in this example, this also could be a big long body of text. It could be an audio recording. It could be anything that's kind of unstructured that you can meaningfully run through a neural network and come out with a vector embedding. Then once we have that vector, we can take that picture and put it into vector space, right? So you can think of that vector as let's say we had a 256 character vector. There's 256 parts of a coordinate. So latitude and longitude, usually an X and a Y, there's 2 coordinates. For the picture, we're going to have 256 pieces of that coordinate, right? And that's going to put it in some sort of vector space. A picture of another cat, the one before, will be close to that one, but a picture of something like a dog will actually be farther away in that vector space. And I know I'm showing 2D here, but it's really hard to show 256 dimensions. 3 is hard enough. But in your mind's eye, picture that this was like a 256 dimensional space, and pictures of cats would be closer in that dimensional space as opposed to dogs or cars. So then the question becomes, how do you query? Now what can you do that, since you've done that and you've put them in space, what can you do? What kind of questions can you ask? Well, one you like to ask right away is, what picture is similar to this picture? So how would we ask the database this question? We put all our vectors into the database, a vector database, and now what can we do? So we're going to ask it a question, and we're going to take our new picture of a kitty, feed it through that same neural network again, and create a new embedding for that picture. Then we're going to send that embedding to the vector database and ask the vector database, give me other embeddings close to this one. And so the green dot represents the new picture, and the black dots are the embeddings from before. So it's going to come back then with results in decreasing distance order, and it's going to have rank 1, 2, 3, and then it's going to actually have a reference to the image that it is closest. Right? We don't actually store the images in the database. All we're storing in the database is the vector, maybe some actual metadata associated with that vector, but you wouldn't store the whole image there. But as long as you have an ID or a URL or something pointing to that picture, you can turn that into which pictures are most similar to the picture you just showed. So what vector databases are all about is questions related to similarity, right? These kind of ambiguous questions, not like equals or less than or greater than, it's things like. That's the kind of questions you want to answer, right, with a vector database. Vector databases are not transactional like a relational database that you're used to, right? They follow more of the base principles rather than ACID. ACID is the relational database. Base is more things like Mongo, Cassandra, where you want to be able to horizontally scale and you want to be eventually consistent, but you don't want to do your banking in those systems, right? They're also not great when exact search use is the dominant use case. So if most of your use cases where you're going to query the database have an exact representation like weight greater than, or amount of CO2 less than, or equal to, or this plus this, where you're going to do those kinds of manipulations, then a vector database is probably not the right answer for that. They're specialized for a particular use case. So you should think of them as like supplemental in your data infrastructure. They're going to be an addition to another tool in your tool belt. You can use them for providing memory for your AI models. So these large language models and all these other models, if you don't store your vectors into a database, then they have to live in memory and you have to keep them running all the time or recompute the vectors next time you start up that model, right? So this allows you to compute the vectors from your large language model or any of the other embeddings that you do, store them in a database and query and use them later for all sorts of other operations and in other models as well. They reduce the cost for running an AI infrastructure, like I said before, because you can actually store the data into the vector database and turn off the LLM if you're not using it at the time. You have all the embeddings, so that's not going to change. But if you're not using that model at that point in time, you can turn it off and then reconstitute that model again using the vector embeddings rather than having to calculate them again. They're also great for horizontal scaling. Because of the base properties that they follow, they are generally horizontally scalable, which makes them really pretty good in Kubernetes infrastructures, where there's horizontal scaling is the mode that Kubernetes expects. So any of those horizontal scaling architectures, they excel in that situation, which also makes them perfect for microservices architecture, where you might have your relational database going, and that's great for your transaction stuff, but then there's a picture, let's say, that's also uploaded with your image, according to some transaction that you stored. You would send that image through the neural network supply chain, store a reference back to the relational database, and then put the vector that came out into your vector database. And that way you can query your vector database really quickly, but you can also then tie it back to the relational information you have. They're complementary. And you can also think of this as an interface between your data scientists and your application developers. Because the data science people are the ones who are going to be actually calculating the vectors, but the query language that's available inside the database is much more friendly for an application developer. So they don't have to become experts in data science or vectors. They can actually just use the vector embeddings to query it and get the answers they want. So some example use cases for vector databases are search, where your search results are ranked by relevance to a query vector, right? Not like an exact find me all if it has these 3 words in it, but you say, oh, I'm putting in this phrase, find me phrases that are similar to this phrase. Clustering. So it's actually really good for, like we showed with the cats, like putting all the cat pictures together and saying that all the dog pictures go together, like that kind of clustering. They're good for recommendations, right? Because you can create a vector out of what the user has currently done before, or a list of the vectors that the person has done before, find them kind of in the coordinate space, and then say, find me other things in that space that the user hasn't seen. They're good for anomaly detections, right? This is almost the opposite of similarity. Basically, you say, be on the lookout. Here's our normal vectors, and anything that's greatly dissimilar or has a really great distance away, that could be an anomaly, right? Diversity measurements, where you look actually at the measures of similarity, like how much diversity is in your data set, how similar. You can look at the distributions and see the distributions of your data sets in space. And classification, right? And this is kind of like clustering, but a little bit more specific, where you actually this is a pretty common example. You feed in a picture of that cat and the system spits back the word cat, animal, like a list of labels that will probably apply to that cat. Right? Those are the use cases. What this means for you is they tend to be horizontally sharded, distributed, so plan accordingly. They do a lot of random reads, so IOPS really matter. The way that you walk a vector database index requires a lot of random reads. Some part of your streaming ingestion pipeline is going to probably handle embeddings. As you start to put structure around this unstructured data when it comes in, you're going to probably send it to a neural network, probably over some eventing framework, and then pick it up, make it into a vector, and then back through that eventing framework, send it into some vector database. On the plus side, they tend to reduce overall data stored in the database. Embeddings are actually a compression. So remember, there was all those bits in the picture of the cat. We turned it into, even the biggest vectors that we see right now are like 2,000, even maybe 5,000 elements in a vector. That's still a lot smaller. It's a single number also. It's not like red, green, blue. So that big picture is going to get reduced to a 5,000 element array. And that's what gets stored in the database. So it's a big compression technique. Given the newer, bigger AI ML push, they're definitely going to be coming for part of your data infrastructure. I think you're probably already seeing this, but just be ready for it if it hasn't happened yet. To sum it up, in ML and AI, vectors refers to the generated numerical representation of unstructured data. Again, it can be structured, but typically now it's unstructured, and these are called embeddings. The vector encodes meaning into a multidimensional space. So it kind of encodes the meaning of that picture into some high-dimensional space that you can then ask questions with. Vector databases allow you to store and query vectors. That was pretty obvious. They handle questions related to similarity. They're usually distributed horizontally. And hang on, it should be an interesting ride. Hope this was informational, and hopefully next year I'll be there in person. Thanks.